Welcome to this video, how to compute and use the tangent plane to a surface. The MatLab programs that we use here are available as in text form in the description to this YouTube video. Let's talk about the goals of this video. First, we'd like to determine the equation of a two-dimensional plane in 3 space, and we'll look at several versions of this equation. Secondly, we would like to use MATLAB to display a plane in 3-dimensional space using computer graphics. And also in the description of this video, I will include the code for this MATLAB program, which you can copy and try yourself. You can also use it in Octave. 3, define what it means for a function of more than one variable to be differentiable. Fourth, let's find the tangent plane to a surface at a point P on the surface. And fifth, let's solve this problem. Suppose for specific values of x and y, we know the value of f of xy. And suppose also for the values of x and y, we want to change them slightly to x plus delta x, y plus delta y. Then we want to solve this problem by use of an easy computation, perhaps one that can just be done by hand without a calculator. Estimate f of x plus delta x, y plus delta y. So basically, we know the value of f of xy. We want to change x and y just slightly and find f of those new coordinates. Why do we want to find tangent planes? Well, first of all, it's a good application of techniques of multivariable calculus. Also, this tangent plane can be used to approximate the value of a function, perhaps much more easily than plugging numbers into a function. We can generate some nice graphics using Octave or MATLAB, and overall, it's just fun. So let's let this normal to the plane have components, the numbers a, b, and c. And let's let v be this vector. And in that case, the vector v has components x minus x naught, y minus y naught, z minus z naught. These two vectors, n and v, are perpendicular. N, remember, is a perpendicular vector to the plane, and this vector v is embedded in the plane, so these two vectors have to be perpendicular. That means that the dot product of those two vectors has to be 0. Well, n dot v equals 0 we can write as the vector with components a, b, and c dotted with this vector v has to equal 0. Now let's remember how we take a dot product. It's going to be this scalar a times the first component of this vector, then second component times the second component of this vector, plus the third component of n times the third component of v equals 0. And so what we get is a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. That followed directly from the definition of the dot product, and also the fact that the dot product of two vectors that are perpendicular to each other is 0. As an example, let's find the equation of the plane containing the point 1 minus 3, 2 and perpendicular to the vector n, which has components 6, 2, and minus 3. Our solution can use what we just found. The formula for that plane in general is a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. A, b, and c are the components of that normal vector, which in this case are 6, 2, and minus 3. So we can write this equation this way. But then x naught, y naught, z naught is this point that we have in the plane. In this case, it's 1 minus 3, 2. So we substitute 1 for x naught, minus 3 for y naught, and 2 for z naught. In the y term here, we have minus a minus 3, which gives us y plus 3. Now, if we multiply all of this out and collect the constant terms together, this simplifies to 6x plus 2y minus 3z plus 6 equals 0. Let's see how we can use MatLab to produce a surface plot of the surface determined by this equation. We should recognize from earlier that this equation is the equation of a plane. So here's the program, PlotTangentPlane.m. First of all, we have 3 statements here that clears the command window, closes all figures with visible handles, and basically clears the workspace of variables and functions. I guess it really clears the symbol table that refers to those. So this is just a little bit of housekeeping to get rid of some stuff that might be left over from running other programs. We'll define x to be the following list. It'll go from x equals minus 8 to x equals 8, 32 evenly spaced values. So this will produce a list. Similarly, we'll let y be a list with elements going from y equals minus 8 to 8 with 32 elements in that list also. Then we will have xy equals meshgrid xy, and that's going to produce a couple lists here. Then z will be 2 times x plus 2/3 times y plus 2. We will then produce the surface using the x, y, and z arrays that were created up here. Hidden off doesn't really have to be here since we never made hidden on earlier, I guess. We'll set alpha to 0.5. That will mean that the transparency will be 1/2. This plane over here, you can see through it. And this statement was commented out. This program, when run, creates this type of image. We could use surf like this, and in the figure window we could actually move this the axes around, rotate them, and so forth, so that we can get other views of this surface. So here is a general formula for the equation of a plane. Some constant times x plus some constant times y plus some constant times z plus a constant equals 0. This will be the equation of a plane as long as a, b, c, and d are not all equal to 0. The general formula for the equation of a plane containing the point with coordinates x naught, y naught, z naught is a constant a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. Now we're going to start looking at another problem related to planes. We're going to look at a surface. It doesn't have to be a flat plane. This surface could have many different shapes. And we're going to consider the function that creates that surface. it'll be a differentiable function. And for a function of one variable, differentiable means has a derivative. When you get to functions of several variables, more than one variable, differentiable does not mean has a derivative. It's a little bit more complicated than that, and we will see what it means. We will find tangent planes to surfaces defined by differentiable functions at a point on that surface. We will say that a surface z equals f of xy has a tangent plane at a point x0, y0, z0 on that plane if f of xy is differentiable at x0, y0. So we now have to ask, what does it mean to be differentiable? As we mentioned before, it means more than just having a derivative or having partial derivatives. We will say that the function of two variables, f of xy, is differentiable at the point x0, y0 if f of x0 plus delta x, y0 plus delta y equals f of x0 plus the partial of f with respect to x at x0, y0 times delta x plus the partial of f with respect to y at x0, y0 times delta y plus epsilon 1 times delta x plus epsilon 2 times delta y. Now the epsilon 1 and 2 can depend on x0, y0, also delta x, delta y, but it has to have the following properties. Epsilon 1 goes to 0 and epsilon 2 goes to 0 as delta x goes to 0 and delta y goes to 0. In that case, we can define a function L. L of x0 plus delta x, y0 plus delta y is f of x0, y0 plus this partial of f with respect to x times delta x plus this partial of f with respect to y times delta y. F and these two partial derivatives are all evaluated at the same point, x0, y0. So this tells us, looking at what we have up here, approximately what the value of f at these coordinates would be. So this function is called the linear approximation or tangent plane approximation of f at the point x0 plus delta x, y0 plus delta y. Okay, this is the formula for L that we just saw. Suppose we decide to call x0 plus delta x just x, and y0 plus delta y, let's call that y. Well, in that case, delta x is going to be x minus x0, and the delta y is going to be y minus y0. So in that case, we can say that L of xy is going to be f of x0, y0 plus the partial of f with respect to x at x0, y0 times x minus x0 plus the partial of f with respect to y at x0, y0 times y minus y0. So the graph of z equals L of xy is a plane. Here's a fact about the differentiability of a function f of two variables x and y. Let's suppose that the partial derivative of f with respect to x and the partial of f with respect to y are both continuous at the point x0, y0, and the partial of f with respect to x and the partial of f with respect to y are defined in an open rectangle R containing that point x0, y0. So here's an open rectangle. That means a set of points, in this case rectangular shape, that does not include its boundary. So a point right on the boundary is not part of R, but something in the interior would be a part of the open rectangle R. And this point x0, y0 is inside R, as shown here. Well, if these two conditions are satisfied by the function f, then it turns out f is differentiable at x0, y0. So the linear approximation of f L of xy we saw could be written as f of x naught y naught plus the partial of f with respect to x at x naught y naught times x minus x naught plus the partial of f with respect to y at x naught y naught times y minus y naught. Well, if we look at these terms up here in blue, we can write this sum, this term plus this term over here, as the dot product of two vectors. The vector whose two components are this and this, dotted with the vector of two components, which is this vector here and this vector here. So L of xy can be written as f of this stuff plus this stuff dotted with this stuff, the dot product of two-dimensional vectors. Well, this first part right here, this first vector, the partial of f with respect to x, the partial of f with respect to y as the two components, is called the gradient of f. And we're evaluating it at the point x naught, y naught. So we have the gradient of f at this point dotted with this vector. Another way that the gradient of f is written is by this symbol right here. This represents the gradient of f at the point x naught, y naught. So let's use this linear approximation formula in a problem. So let's let f of xy be the square root of x plus the square root of y. Then if we look at f of 2, 4, that is the square root of 2 plus the square root of 4, square root of that whole thing. That's just the square root of 2 plus 2. Square root of 4 is 2. So f of 2, 4 is equal to 2. Let's approximate f of 2.03, 4.05. So in this formula up here, x naught, y naught is going to be 2, 4, and x comma y is going to be the 2.03, 4.05. So we'll let L of xy be f of 2, 4 plus the gradient of f evaluated at 2, 4 times the vector 2.03 minus 2, 4.05 minus 4. This stuff right here is the vector x naught, x minus x naught, y minus y naught. So that then becomes f of 2, 4 plus the gradient of f at 2, 4 times this vector. This first component is this difference. The second component is this difference. Now, to calculate the gradient of f, we need to know what the partial of f with respect to x is, and also the partial of f with respect to y. So let's start with the partial of f with respect to x. F of xy, remember, is, where is it up here? Right here. If we write this in terms of powers, we'll have the quantity x plus y to the half all raised to the 1/2 power. So the partial of f with respect to x is the partial derivative with respect to x of the quantity x plus y to the 1/2 raised to the 1/2 power. Now use the chain rule on this, and we'll get 1/2 this stuff to the minus 1/2 power times the derivative of this interior stuff, which is right here. Now the derivative with respect to x of x is 1, and the partial derivative with respect to x of y to any power is 0. And so this derivative right here is just 1 plus 0, which is 1. So it simplifies to this. So what we can then say is the partial of f with respect to x equals, and then we'll evaluate this at 2, 4. So plug in a 2 for the x, a 4 for the y, and so that's what we have right here. 4 to the 1/2 power is 2. And so this stuff inside is 2 plus 2. So we have 1/2, 2 plus 2 raised to the minus 1/2 times 1, which is what we have right here. Now, 2 plus 2 is 4. 4 to the minus 1/2 power is 1 over the square root of 4, which is 1/2. So this stuff right here is 1/2 times another half, which equals 1/4. So now let's find the partial of f with respect to y. So it's partial derivative with respect to y, and this stuff right here is f. Once again, using the chain rule, we'll get 1/2 this stuff to the minus 1/2 power times the partial derivative with respect to y of this stuff. Now the partial derivative with respect to y of x is 0. The partial derivative with respect to y of y to the half is 1/2 y to the minus 1/2. So this stuff right here equals this first factor, which is right here, times this derivative, which is 1/2 y to the minus 1/2. So then, substituting in x equals 2 and y equals 4 into this formula right here, we get 1/2 2 plus 4 to the half raised to the minus 1/2 times 1/2 4 to the minus 1/2. Now let's see what we have here. This stuff right here is 2 plus 2, which is 4. 4 raised to the minus 1/2 power is 1 over the square root of 4, which is a half. So what we have here is a half times a half times a half times a half. And that is 1/4 times 1/4, which is 1/16. So that gives us the partial derivative of f with respect to y at 2, 4. Its value is 1/16. So going back to our approximation formula, L of 2.03, 4.05 is f of 2, 4 plus the gradient of f at 2, 4 times 0.03, 0.05. We saw that before. And so what do we have? F of 2, 4 is equal to 2. The gradient of f at 2, 4 is this vector 1/4, 1/16, and we have the dot product of that with 0.03, 0.05. So what do we have here then? We have 2 plus, and then this dot product is going to be 1/4 times 0.03 plus 1/16 times 0.05. So that simplifies to 2 plus 0.03 over 4 plus 0.1 over 16. If we look at this second component times this second component, we would have 0.05 divided by 16. And so what we get is 2.010625. If we check with the calculator the value of this function, square root of 2.03 plus the square root of 4.05, you get 2.10587, which is pretty close to what we have right here. So we have a pretty good match in the approximation and a more exact calculation with the calculator. In a way, this is an approximation too, because our calculator only holds a certain number of significant digits. What we just did is called a tangent plane approximation of f. Why is this the case? Well, if we look at that linear approximation formula, L of 2 plus delta x, 4 plus delta y is f of 2, 4 plus the gradient of f at 2, 4 times delta x, delta y. And so we can remember that for our particular function f, this gradient of f at 2, 4 was the vector 1/4, 1/16, and the rest remains as before. Now going to the third line, we remember that delta x, delta y is x minus 2, y minus 4. That's how much x changed from 2 and how much y changed from 4. So we get this. And then if you just write this out, z, which is L of xy approximately, is f of 2, 4, which is 2, plus a fourth times this component, plus a 16th times this component, which is what we have right here. So our approximation then is z equals 2 plus a fourth x minus 2 plus 1/16 times the quantity y minus 4. And if we look at this, this is the equation of a plane. And why is that the case? Well, if we rewrite this equation in the following form, this term 1/4 x minus 2 plus this term 1/16 y minus 4, and then if you subtract z from both sides, we can write plus minus 1 times z minus 2 equals 0. This we get by subtracting z from both sides of these equations and combining these two into a minus 1 times z minus 2 term, which we have right here. And we notice that this is in the form a constant times x minus x naught plus a constant times y minus y naught plus a constant times z minus z naught equals 0. And we recognize this as the general equation of a plane. This plane is tangent to the surface z equals f of xy at the point xyz equals 2.2, 4, 2, and that's why it's called a tangent plane approximation. Here is a MatLab program to plot the surface we've been investigating and the tangent plane to that surface at the point 2, 4, 2, x, y, and z being 2, 4, 2 for the point of tangency. So, besides this comment here, which we'll skip for the time being, we clear the workspace of any variables that might be there already, just in case we ran previous programs. We define a figure, it's going to be figure 1. We let x equal linspace 0, 5. That creates a one-dimensional array starting at 0, ending at 5, and it will have 100 elements in it. Y equals linspace 0, 5 does the same for creating an array y. Then capital X, capital Y equals meshgrid xy. This will create, as we saw before, arrays x and y. We will let z be the square root of x plus the square root of y. We'll turn hold on and we'll draw the surface x, y, z, defined by this equation right here. And then we will plot the point 2, 4, 2 as a red asterisk. That's going to plot the point of tangency. Then we'll plot the plane. So we have z equals 2 plus 1/4 times x minus 2 plus 1/16 times y minus 4. Since we're using array elements, doing array operations, we'll use a dot times here, a dot times here. In this particular case, the dot's probably not necessary because we're just multiplying it by a scalar, a number here. So we could have just had 1/4 times x minus 2, and we could have also gotten rid of this dot here. Then surf x, y, z will make a plot of our tangent plane. On the axes, we'll put x labels of x, y, and z, and then hold off. If you notice, we had hold on here, hold off here. So everything between here and here, which basically makes two plots, will be shown on the same axes. So we'll see the surface, we'll see the tangent plane, and we'll also see the point of tangency, which is 2, 4, 2, which we plotted right here. When we run this program, this is what we see. I made one slight change in the program when I ran it a second time. Instead of a red asterisk, I decided to make it a white asterisk, so it shows up a little bit better here. We can see that white dot right here. If we come over here, we can rotate things. Whoops, let me try this. And here, for instance, we can see that flat plane, and here we see that surface. And if we go perhaps like this, we can perhaps see that we have the surface here, we have the plane here, and the two touch each other at this one point, which is right here. It's possible that there are some other points where the two touch, but they are tangent at least here. We could do some further analysis to find out if they touched anywhere else. My guess is probably they don't, but I'm not sure. Haven't really thought about that. As an application, let's look at the following problem. A metal box has a square base, each edge 3 inches long. The height of the box is 1 inch. This is illustrated over here. This side is 3 inches, this side is 3 inches, this height is 1 inch. The block is heated and the base edges expand to 3.02 inches and the height increases to 1.01 inch, as we see in this picture here. Let's use the tangent plane approximation to approximate the volume of this expanded block. So let's look at the solution to this problem. We want to find the volume of this expanded block. We can think of it as being expanded, starting with this block. So first, let's remember that the volume in terms of x and y in this case is x times y, which is x squared y. If you look at this, v of 3, 1 is easy enough to calculate in your sleep. 3 squared times 1 is 9, so no problem. The volume of this box is 9. How does it change to get the volume of this box? Well, we can use our tangent plane approximation. V of x plus delta x, y plus delta y is approximately v of xy plus the partial of v with respect to x at xy times delta x plus the partial of v with respect to y at xy times delta y. So let's plug in what these things are. V of xy is x squared y. The partial of v with respect to x, if you take the partial derivative of this with respect to x, you just get 2xy, and it's multiplied by delta x. What about this partial of v with respect to y? Well, the partial of v with respect to y is just going to be x squared times 1, and so we just get x squared, and it's multiplied by delta y. So now we're ready to start substituting in some numbers. So we'll let x be 3, let y be 1, because v of 3, 1, remember, was very easy to calculate. And according to this approximation formula, v of 3 plus 0.02, the delta x, 1 plus 0.01, the delta y, is what? X squared y is 3 squared times 1. 2xy is 2 times 3 times 1. Delta x is 0.02. Plus x squared, which is 3 squared, times delta y, which is 0.01. And if you look at these terms, this one is 9 times 1, which is 9. This one is, let's see, 6 times 0.02, and so that's 0.12. And then the last term is 9 times 0.01, which is 0.09. And so adding those together, we get that the volume of this expanded block is approximately 9.21. Let's get a more precise calculation of the volume of that expanded block. V equals x squared times y, where x is 3.02 and y is 1.01. So I think I'll start by, in the MatLab command window, typing x equals 3.02 with a semicolon, y equals 1.01 with a semicolon. The semicolons suppress the echoing of basically those commands when the evaluation is done. Now we'll calculate the volume. V equals x squared times y. And I'm not going to put a semicolon after this because I want to see the result of the calculation of V. So I'll hit enter, and it tells us that V is 9.211603, and then a whole bunch of nines. This is in what MatLab or Octave call long format. If you look at this, we have a 3 here and a lot of nines. I think this probably would round off to just 9.211604. And the fact that we got a bunch of nines here kind of indicates to me that we had just a little bit of error due to the fact that the values of x, y, and v could not be stored in the variables exactly because they were stored in binary form, base to arithmetic, basically. So what was the advantage of using the tangent plane approximation? Well, we saw that the approximation of the volume did not even require a calculator. It was just a simple case of multiplying some numbers together and performing an addition. The approximation was a quick, easy way to do the calculation using only your hand and brain. Here's a short summary of what we have seen in this video. We saw that the equations of a plane were basically a normal vector dotted with this vector equals 0. This could be written out as an algebraic equation, which we see right here. We said that a function f of xy is differentiable at x0, y0 if it satisfies this equation where epsilon 1 and epsilon 2 both go to 0 as delta x goes to 0 and delta y goes to 0. We saw that a differentiable function has a tangent plane. Basically, if a function f of xy is differentiable at ab, then the surface z equals f of xy has a tangent plane at the point on that surface a, b, f of ab. The approximation, tangent line approximation, can be written this way in terms of x0 plus a slight change in x, y0 plus a slight change in y equals approximately f of x0 plus a couple correction terms. We can rewrite this if we let x be this stuff up here, y be this stuff up here, then we can find out pretty easily that f of xy is f of x0, y0, approximately equal, plus the partial of f with respect to x at x0, y0 times x minus x0, plus the partial of f with respect to y at x0, y0 times y minus y0. I hope you enjoyed this video. Have a nice day.